Now about today's speaker. Dr. John Krupczak is a professor of engineering at Hope College. He began his journey at Williams College, home of the Ephs, in honor of Colonel Ephraim Williams. And where is it located? Of course, in Williamstown, Massachusetts. He received a bachelor's in physics there. And by the way, Williams College claims to have played the very first intercollegiate baseball game against its arch rival, Amherst College, in 1859. We may have to dig into that allegation after the presentation. Our speaker went on to the University of Massachusetts in Amherst and received master's degree and a PhD in mechanical engineering. He worked for 5 years at Verizon and the Department of Energy before joining the faculty at Hope College in 1994. In 2000, he became the director of Hope's engineering program. At the time, it was a part of the physics department, but it seceded from there. And in 2006, it became his own department, which he chaired until 2013. Our speaker is an accomplished educator. He was the founding chair of the Technological and Engineering Literacy Division of the American Society for Engineering Education. He's been a senior fellow of the Center for the Advancement of the Scholarship of Engineering Education of the National Academy of Engineering. He was the faculty advisor of Hope's student chapter of the National Society for Black Engineers at its founding in 2006. He was voted Hope Outstanding Professor Educator by the graduating class of 2009. And from 2013 through 2016, he served as a program director in the Division of Undergraduate Education of the National Science Foundation. He's also an accomplished author. He contributed to 30-Second Engineering, 50 Key Principles, Methods, and Fields, explained in half a minute. Half a minute each, not for the whole thing. He also authored Philosophy and Engineering Education, New Perspectives, an Introduction, and last year, Springer published Understanding Technological Systems, a book for non-scientists of which we will hear of today, I'm quite certain. His teaching focuses on 2 courses at present, an Introduction to Engineering and the General Education course, Science and Technology of Everyday Life. That's a course in which non-science majors use physics and engineering lab equipment to better understand things they use routinely, like microwave ovens and automobiles. His current research focuses on energy applications of photothermal materials. And since 1997, he's received more than $2 million in research grants from agencies beyond Hope College. And finally, many of us know people who have multiple cats as pets. Dr. Krupczak is among them. Maybe we need to find out if there's a symbiotic relationship between his cats and his rooster, which he also has. I'll leave it there. Dr. Krupczak, it's up to you. Thank you so much.
Thanks, Louis. Thanks for the generous introduction. So I'll explain a little bit about the cats. So we live in Lake Town on the last house before the road gets pretty unpopulated. It seems to be a good place for people to deposit their unwanted pets. So I think that's how we've accumulated at least 2 of the cats, and for sure the rooster, who hangs around in our backyard. And we're not sure how long we're going to be able to keep him because, as some of you may know, when roosters grow up, they get a little aggressive, and he's chasing the bike riders going by. So we're going to have to do something about that pretty soon. But thank you so much for inviting me to speak to you at the Academy here. And I was thinking this is actually a rare occasion for me to have a voluntary audience. So and I'm not sure I can live up to the expectations as opposed to a normal class situation where the students are compelled to be there one way or another. But we'll try. So I also want to introduce Kathy Brooks, who's my wife, and is going to be helping out with some of the demos. Great. So our topic is understanding technological systems, and we might think this is a bit of a challenge. Arthur C. Clarke has made this statement, any sufficiently advanced technology is indistinguishable from magic. Some of you may be familiar with Arthur C. Clarke's work. One of his most well-known is the writing of 2001 Space Odyssey. But what do we mean? What does he mean by this? Well, magic, things like a magician pulling a rabbit out of a hat, and technology like the mobile phones and all the other devices that we rely on and use every day. So Arthur C. Clarke is making a comparison between these two. In some ways, they don't necessarily seem related aspects of our everyday life. But delving into the comparison a little bit, I think what Arthur C. Clarke is referring to is magic, like the magician pulling the rabbit out of the hat, has the surprising, unexpected, remarkable result, and the audience has no idea how this is accomplished. That's really the charm of the magic. And whereas technology, we could say it similarly has a remarkable behavior. Pick up the cell phone, produces videos, text messages, all sorts of entertainment. And just like pulling the rabbit out of the hat, we really have no idea how it does it. So in terms of our work today, we can use the comparison between magic and technology by noticing that in magic, there's an explanation. There's usually a key step that if we understand how that step takes place, then we understand how the magician accomplished the magic step. Similarly, in technology, there is an explanation. These things were made by people. So just like the magician, somebody knows what they are doing. And we can understand as well if we can identify frequently one or two key hidden steps to understand how the technology does what it does. So if we're going to understand magic, like the rabbit being pulled out of the hat, a few key aspects of how the magician does what they do. First, there's the preparation step. And typically in the rabbit out of the hat, various magicians have their own take on this, but the rabbit is usually hidden somewhere before the trick begins and involving typically some kind of specialized equipment or costume. There's the misdirection. So the magician is showing the empty hat, he's directing the audience's attention to something other than where the rabbit is. Then at some point, the magician, typically an assistant, will deposit the rabbit in the hat. The magician then retrieves the hat from the assistant, reveals the bunny, and the audience is mystified. Now, another key thing about magic is the magician and typically the assistant practice the technique. So they practice it over and over again. So there's no mistakes. And magicians as a profession rarely, if ever, voluntarily disclose their technique so as to keep it hidden from the audience. So just a quick specific here, without going too much into this. So two well-known musicians, Penn and Teller, did pulling the rabbit out of the hat on a Jimmy Kimmel show. And what I'm showing you here is the actual moment when the assistant, Teller on the right, is depositing the rabbit in the hat while the magician in the middle, Penn, is misdirecting the host, Jimmy Kimmel, and the rest of the audience by twirling the baton. So he's twirling his magic wand. He's waved the hat around, showing everyone that it's empty. He puts it down at his side. The assistant, Teller, takes the rabbit from a pouch behind him in his coat, slips it into the hat. Penn, without even looking, grabs the hat, pulls it up, reveals the rabbit. So there's a technique to it. And by looking at it, by noticing that, okay, there's a key step here. If we understand that step, we understand the magic. So in terms of understanding technology, I'd like to suggest we can use 5 main ideas to help us demystify and make some sense of the magic of our technological devices. So and this, as Lewis mentioned, this approach was developed through a class I've been teaching at Hope College since I started here in 1994 called Technology, Science and Technology of Everyday Life, and specifically aimed at non-science majors. So one of the key challenges I had in teaching the course is, well, how do we organize this material for an audience that doesn't necessarily have the usual prerequisites that science students would have? And what I came up with after a fair amount of trial and error is organizing around these 5 key ideas. So, and I'll explain these more as we go along. So one is the idea of a system. The next is the idea of a component, a system element. The third important idea is that components do what they do by utilizing some principle of science, some physical effect. The ideas of form and function, and how form, the nature of a particular object, makes the function possible. So just listing these, and I'll explain them hopefully as we go along. So what I'm going to do is define these 5 main ideas, and then we'll look at some examples of how we can use this approach and a few key ideas to understand some familiar technologies. So first, system. So system is something, it's a word in everyday vocabulary, but we need to be a little bit specific about what we mean by a system, hopefully in line with our intuitive understanding of a system. So one definition of a system is a group of objects forming a network that interact to achieve a common purpose. So examples might be a subway system, circulatory system in your body, a river system. And we're going to say that technological objects can be considered as systems, a group of elements working together to achieve an overall purpose. A key advantage here is if we use a system approach, then we can focus on one part of the system rather than trying to understand the whole thing at once, and then build up our understanding from an understanding of the elements. So just an example here of a natural system like the Mississippi River system. So it's composed of all the streams that feed into numerous rivers that then feed into the Mississippi River to create an overall interacting network of water flow that is the Mississippi River. Another example is the circulatory system in our bodies. So this consists of a number of elements that interact to achieve the overall purpose of circulating the blood to provide oxygen to the cells and remove carbon dioxide. So it includes things like the heart, the lungs, the veins and arteries, the capillaries, the blood itself. And this is our circulatory system, accomplishing one of the several functions that our bodies need to be sustained. So if you look on the right, so that's a map of the Washington, D.C. Subway system, the metro, and it shows, so what does the metro system consist of? So it's the track, it's the trains, it's the stations, it's the people that run the trains, the fare taking apparatus. What do you need to understand the DC metro system? So as a user, you typically don't need to understand the entire system. So as a user, what do you need to know? You need to know your station that you want to get in at, the station you want to leave from, the schedule. So by studying a part of the system, we can gradually develop greater and greater familiarity with the overall metro. So we're going to be using this framework as a key aspect of understanding different technology. So quickly, there's a key aspect of the system compared to what's called the collection. So in a collection, like many of us have one or more drawers like this around, like us, Kathy, pretty much every drawer in our, except the cat food drawer, that's pretty well organized. So there's a bunch of things in there. It's a collection. There's not an apparent interaction for some greater purpose or some net outcome. Now, if you look at technology, so things like the smartphone, the bicycle, MRI scanner, or a paper mill. So we can use this framework to characterize all these different technologies. So something like a smartphone, which obviously has lots of internal components that are interacting to achieve its overall function, fits the system description. But even a bicycle, so relatively, in the scheme of things, relatively simple technology, involves a number of components like the pedals, the chain, the gears, the seat, the handlebars, the bearings, that are all interacting to achieve the overall purpose. And not just consumer technology, so something fairly remote to our everyday lives, but something important that we all use paper in one way or another. We can consider a paper mill to be an interacting system of components. Okay, so a little bit about the components. So the components are the elements of the system. The components interact with other components, and as we'll get into in some of the examples, at the component level is where we can identify the natural phenomenon or the principles of science that are put to work that allow or enable the component to do what it does. Furthermore, a key aspect of technology is that components in one system can be used in another system. So like a motor, wheel, don't reinvent the wheel. What that's getting at is a component that provides a useful function can provide that function in numerous systems. Furthermore, so this is the idea of the magic, is we put these components together, the sum is greater than the parts in some ways. So one way to think about it. So there's a hairdryer. If we open it up, we see all the parts, but as a system, these components are interacting with the other components to achieve the overall function. And just like a team, T-E-A-M, together everyone achieves more. When the components are working together as a team, the net result of a hairdryer, in some ways, to humans has more utility than the individual components like the switch, the motor, the heater, and the fan on their own. And we mentioned how the components can be reused. Just think of like the switch. So it performs a useful function of actuating current, and we can use this in a variety of systems that have a need for this particular function. Okay, last key idea before we get into an example, the concepts of form and function. So what do we mean by this? And probably something that you may have run across in other aspects. So form in this context we'll use to describe the physical properties of an object, what it is in a sense. So let's take a fairly simple object like a rock. Let's start with something fairly basic. The form would be the size of the rock, the shape, the chemical composition, some of its properties like fracture strength, color. Think of it as that's what the rock is. Function is what we can do with the rock. So we could use it as a hammer. It could be a weapon. It could be a construction element in a wall or a building. It could be a paperweight. And the idea here is that the physical properties, the form, like the weight of the rock, make possible the function, what it can do, like acting as a paperweight. Notice that any given form, like a rock, can have a variety, you might even say an infinite number of functions, and lots of things we can do with a rock. Okay, questions so far? Pop quiz? Not yet. All right, here we go. So let's jump into this. Let's go over something somewhat familiar in our everyday life, like the jet engine. So we think about air travel. It's magic, totally magic. Board the plane, get in. Maybe not always as magical as we'd like. You close the door, it takes off. A couple hours, you arrive, in Florida or wherever. Magic. How does it do that? Okay, so a few things here. Then we'll get into the jet engine. So first, in terms of the airplane, so when the plane is in the air, we can think about its behavior as the balance between four key forces. So starting off with one force, the weight. So the weight, the attraction of gravity, the Earth's gravity on the plane results in a downward force, would keep it on the ground. Okay, so for the plane to be airborne requires a force to be at least equal to the weight pushing up, we call the lift. So in stable flight, lift has to be greater than or equal to the weight. What about the other direction? The horizontal direction that's going to get us from here to Florida. Well, the air resistance on the moving plane is the drag that would slow the plane down if it weren't overcome by an equal force of the thrust from the engines. So if you throw a baseball, unlike throwing a baseball on the moon, it will eventually slow down due to air resistance if it doesn't hit the ground for some other reason. So for the airplane to travel horizontally, we need to have a source of thrust that is equal to or greater than the drag on the airplane. And we also need thrust to accelerate the plane from a stop. I just want to quickly mention on the plane, the wing is well known to provide the lift, provide the vertical force. And the characteristic shape of the wing interacts with the oncoming air to result in a force basically perpendicular to the plane of the wing pushing up. So we're going to leave the wing and move on to the engine, which provides the thrust. So what do we know about the engine? We look at the engine sitting there, in the airport, waiting to board. Well, it's probably our plane. You see the engine there. So how does that thing provide the thrust? Well, the thrust of the engine is the basic effect is really like a balloon. So if you blow up a balloon and let it go, what's going to happen? The balloon's going to be propelled around because of the force exiting the balloon. The stream of air coming out the back of the balloon results in a force in the opposite direction that pushes the balloon forward. So we're going to try to demonstrate that here with the help of my able assistant. Just give us a second. All right. So we have a plane, and we're going to secure the guide wire here. I have a balloon. So what I'm going to do is blow up the balloon, then I'm going to Velcro it to the bottom of the plane and let the balloon go. And hopefully we'll see that the exhaust from the balloon will push the plane forward. We'll see how that goes. So unlike the magician, there's no special trick here that my assistant is accomplishing here while I misdirect you. All right, so there's the balloon. All right. Didn't quite make it to the destination, but hopefully demonstrates the idea. Thanks. So the jet engine is really just a continuous balloon, a big balloon that's producing a continuous stream of air out the back of the engine, resulting in a force pushing the plane forward. So just like the balloon in our demo here. So how does it do that? How do we result in a balloon that essentially never deflates, constantly pushing air out? So this is the view of the engine we normally have sitting around the airport. We take the cover off, it looks something like this, lots of wires and tubes, looks complicated. We remove some of the distracting background. It still looks like a lot going on there. But in terms of the jet engine system, really can be thought of as having four main components, four key components that work together to result in a continuous stream of high-speed air out the back to produce the thrust. So we'll look at each of these components in turn. So there's the fan at the front of the engine. That's the part you normally see that draws in air. There's a compressor that's used to increase the compressor section here, increase the pressure of the air. The combustion region where the air is burned with fuel to produce a continuous stream of exhaust out the back of the engine. That's producing the thrust. And then there's the turbine, which is used to capture some of the momentum from the exhaust and turn the compressor and the fan. So that's how they all work together. We're going to look at each one separately and see how their form enables the function. So the fan in the jet engine is really, just a bigger version of our, usual fan here. You can see the shape of the blades, the jet engine fan, similar to any household fan, maybe more of them a little bit bigger. When the fan rotates, the shape of the blades deflect the air along the axis of the fan. So, but unlike a home fan, so a home fan, you usually direct the air coming out. On the jet engine, the fan's facing the other way. It's sucking the air in and pushing it into the engine. So step number one. Okay, so the next, and I think this is one of the cleverest components of the jet engine, is the compressor. So looking ahead, we need to have a bunch of air available to provide oxygen with the fuel. So we need some way to increase the amount of air available, and that's done with the compressor. So if you're having a campfire and it's not quite catching, what do? You start hopefully waving something, fanning the flames. Why are you doing that? Well, you increase the flow to increase the amount of oxygen available, maybe encourage the combustion. So the jet engine, the way that the compressor increases the amount of air available is by pushing it into a smaller and smaller region. So there's similar to fan blades that push this air, and notice it's getting pushed into a smaller and smaller space. So the density of the air and the pressure is increasing as these compressor blades push it into a smaller and smaller space. So by the time it gets to the combustion chamber, we have a concentrated amount of air available to burn with the fuel. So we're halfway there. So next, and then, this picture here is an actual GE jet engine, and you can see hopefully how the compressor blades, so they start off here, see how long they are, and then the blades get shorter and the base of the engine gets wider, so the air gets forced into a smaller and smaller area, increasing its pressure. See, no magic really. Then we have to burn the fuel with the air to create a stream of gas coming out the engine. So like the continuously exhausting balloon is produced by burning the fuel with the compressed air. So the combustion region is really just like a propane torch, burning the air and fuel, sending it out the back. So this is like our continuously deflating balloon. We have one more component. So we have our stream of gas pushing the plane forward, but we ask one question. The plane's flying, it's not connected to anything. What's turning the fan and the compressor? The answer is the turbine. So another clever aspect of the jet engine. So the turbine is basically the same principle as a windmill. So I have like a pinwheel here, and if we have a stream of air causes the pinwheel to rotate. So the turbine in the jet engine is in the path of the exhaust gases. So you can see the blades there of the turbine, similar to a pinwheel or similar to a kind of a metallic version of a windmill, are rotated by the exhaust. And then the shaft there that you can see on the left is connected back to the compressor and the fan. So when the turbine is rotated by the exhaust, it in turn is what's turning the compressor and the fan. So the turbine is what in some ways powers the fan and the compressor. So now we can see the entire jet engine here with the fan drawing in the air, compressor compressing it, the combustion chamber where we burn the air and fuel, resulting in a stream of exhaust, and then the turbine, which is placed in the exhaust stream to provide some mechanical power back to the compressor and the fan. So you'll notice these all these components are on the same shaft. So when the turbine is turned, it turns the compressor and the fan. So that's it. That's the jet engine. That's how we get to Florida.
This part is intuitive and I understand it. And so you're demonstrating a turbojet. But most jet engines nowadays are turbo fans. Why would the fan in front produce so much more of the thrust than the hot side of the engine?
Yeah, so my understanding is the turbo fan, which has a bigger, part of the reason for the turbo fan to having a bigger fan is it makes the engine quieter and also helps with cooling the engine. So some of the key components can operate at higher RPM because they're more effectively cooled by the extra airstream. But it's the same basic principle. It's a variation on the standard jet engine.
This may be intuitive, but I'm wondering, when you get to these Mach speeds, is it fuel related? Is it design related? Any of both maybe?
Mach speeds?
Faster speeds with these jets.
Right,
Anything
so-
change?
Really good question. So why can't we fly a plane into space? It relates to your question about Mach speeds, is that the jet engine, the oxygen to burn with the fuel is drawn in by the fan. So as you go to higher altitudes, the density of oxygen goes down, so it's harder and harder to get in the air that you need. So one of the limitations with to fly faster, like higher speeds, Mach speeds, you need to create more thrust. So you reach a point where they can't draw in enough air to produce the thrust needed to have enough velocity to reach the Mach speed. So it's primarily air density limited. Yeah.
Just
All air intake into the jet engine has to be subsonic. You cannot have supersonic air going into the engine because you will create shock waves that will create stall in the engine. So it has to be subsonic going in. So the airplane can be supersonic, but the engine has to be subsonic. So if you ever look at like a fighter jet, they have a blade that creates a resistance that brings the speed of the air intake to subsonic speeds. For the airplane to go supersonic, the wings have to be swept back and the shock wave has to be pushed to further back in order to go through the through Mach 1. Actually, you reach it subsonic because at like 0.95, 0.98, parts of the wing will be supersonic.
Great.
Is that what you're asking?
Yeah, so just like basically kind of getting off track here, but like in an automobile, like the NASCAR racers, and their problem is actually getting enough air into the engine to burn with the fuel. And the jet engine has the same issue as we get to higher speeds and higher altitudes, is actually getting enough oxygen in to combust the fuel.
Just
One-
a
one
fun
point-
curiosity point, on aircraft carriers, when we flew third generation fighters for the F-4 Phantom, it was a turbojet, so you had quick response to the throttle. When we switched to turbofan engines in the F-14, there was a delay, which means you settled coming aboard the aircraft carrier, and so you had to anticipate what the plane was going to do to stay on glide slope. Just a curiosity thing.
Yeah, I think actually you got me. That's kind of a nuance of the jet engine performance I'm not that familiar with, but it sounds like the turbofan introduces a little bit of a lag in the engine. So let's move on from jet engines to maybe a bit more domestic application, the refrigerator. So it's magic. It's totally magic, right? You plug it in, you close the door, it gets cold inside. Anything you put in there gets cold. As long as it's plugged in and we don't have a power failure, we're all good. Okay, so how does it work? So we're going to do a little demo here. I'm going to ask Kathy to pass around some of our favorite liquid here, being sarcastic from the pandemic, hand sanitizer. So you probably noticed this, but I'll invite you to try it again today just to be more aware of the effect. So if you put some hand sanitizer on your hand, rub it around a little bit, and then if you wave your hands slightly, notice it gets noticeably cool. And you probably have experienced this just yourself, trying to get this junk off of your hands when you've had to use it. Yeah, so why is it causing your hands to get cool? It's the principle of evaporation, and it's the same effect that the refrigerator uses for keeping our food cool. So the transformation from liquid to gas requires energy. We have to break the bonds that hold the liquid together. So the hand sanitizer gets that energy from your hand. So when your hand loses energy, its temperature goes down, it feels cool to you. So this effect of the evaporating liquid causing a lowering of the temperature of the surface that the liquid's attached or sitting on is actually what led to the invention of the refrigerator by a printer in Australia so this was 1837, pretty much everything we have today except the printing press. And as some of you may know, they use metal keys where they put the ink on and impress onto the paper. Well, after a while, these keys would get clogged with ink and the printers had to clean them. They used ether, which is a similar chemical to hand sanitizer. And the printer noticed as he was cleaning the keys, they were getting cold. And this was the aha moment, actually recognized that this effect can be used for cooling below room temperature, this evaporation effect. So the challenge we have is similar to the balloon. How do we make this a continuous process? So you use a little bit of hand sanitizer, it evaporates into the atmosphere and it's gone. So in the refrigerator, we need somehow to utilize this effect, but somehow make it a continuous process. We don't need to replenish the evaporating liquid. So the refrigerator system, we can think of it as having five main components, each carrying out an important function in the overall behavior of the system. So first, there's the liquid, the equivalent of the hand sanitizer, the refrigerant. So this is what evaporates and transports the heat. So then there's four main components that are involved. So there's the evaporator. So that's the part that gets cold. So that's where the liquid is evaporating. So in your home refrigerator, there's the evaporator that's usually hidden behind some sort of plastic material. That's the cold part. That's what makes the air inside the refrigerator cold. That's where the refrigerant evaporates and absorbs the heat. But now we need to recover that evaporated refrigerant, turn it back into a cold liquid so it can be a continuous cycle. And that's the function of the other three components. So there's a compressor that's going to compress the evaporated gas, typically located in the bottom of the refrigerator. That's the part that makes noise when your refrigerator is running. Then we have to get rid of the heat through the condenser, which is going to release the heat that was absorbed from the inside. It's going to release it to the outside. And then lastly, this component called the expansion that's going to reduce the pressure of the refrigerant, get it back to its original condition. So we're going to look at these four components, how they do what they do. So just another illustration here, a little bit less detail to point out that there's these four key components. So and for the most part, we really don't see any of them when you use a refrigerator, or you shouldn't see them. The evaporator coils, the cold part, the compressor, usually on the bottom to compress the evaporated gas, the condenser, usually on the outside to get rid of the heat, and then the expansion to reduce the pressure. Okay, so let's look at each one of these and demystify them, understand the magic a little bit. And what I like about the refrigerator is it's really a pretty straightforward example of how form follows function, how the physical shape, configuration makes the function possible. And let's not make it any more complicated than it needs to be. The evaporator is just a tube that contains the refrigerant. Now, to have enough contact area with the air in the refrigerator, it typically kind of snakes around in a serpentine path and may have some metal fins on it to help increase the surface area to contact more air. But a key thing is that inside the evaporator, as the name, they even help us out by naming it with the effect that's occurring. The liquid refrigerant is absorbing heat from the air in the refrigerator and evaporating. So going from liquid phase into gas phase. Molecules are less closely associated. So the rest of it is just making it into a continuous process. So the compressor in the refrigerator is a little different approach than the compressor in a jet engine, but it has the same purpose to increase the density, increase the pressure of the now evaporated refrigerant. So we want to get that back and reuse it. Step number one is we have to crunch it down and increase the density. So the compressor in your refrigerator, it's about the size of a small watermelon, maybe a small pumpkin. It's typically in the back, so you don't see it. But inside there is usually some sort of a piston arrangement that compresses the gas using a little bit different principle. But the same idea, we want to get the gas into a smaller volume. So but like the magician's trick, there's a clever aspect to it. So there's a flap here. So when the piston goes down, the refrigerant gas pushes the flap open to allow the gas to come in. So it's sucking in the gas. And then when the piston starts to go up, the pressure closes the flap. So the gas traps itself in that space. Like, oh no, we're trapped in here. And we've trapped ourselves. And the piston goes up, but there's another flap that opens at a higher, requires more force to open it. So when the gas gets pushed up to the top at a higher pressure, then there's enough pressure. It's like, okay, guys, if we all push on this flap, it might open. And it does, letting the gas out. So it's a different way than the jet engine, but the same effect is to increase the pressure. So we've got the molecules closer together, but they're still a gas, and they actually get hot in this process. Your compressor of the refrigerator usually gets a little warm. Okay, so we got to get rid of that heat. So that's the next component, the condenser. The condenser is the inverse of the evaporator, and the name tells us what it does. It condenses. So what does that mean? It means we turn the gas into a liquid. How does it do that? Well, we need to get rid of the heat that is contained by the gas. And it does this by exposing the gas to a cooler temperature, which happens to be room temperature. So a key point here is in the compression, the gas heats up above room temperature. So then if we go to the condenser, which is now outside the refrigerator, the warm gas will lose energy to the room because it's warmer than the room. So the condenser is pretty much the same form as the evaporator, just used the other way around. So the gas goes in there at high temperature, loses energy to the room, turns into a liquid. So it's condensed. It's gone from gas back into liquid. Now in your refrigerator, this is frequently in the back of the refrigerator. So if you've ever reached around the back of the refrigerator and see something like this and notice that it's warm, like, why is my refrigerator warm? It's supposed to be this part because that's the condenser losing heat to the room. So if you reach around the back of the refrigerator and it feels warm, now older refrigerators, this is exposed. Some newer refrigerators, they put like a plastic panel to hide this. Takes all the fun out of it, some refrigerators have it in the bottom. So if you've ever gone to the refrigerator like barefoot and notice that there's warm air blowing on your feet, it's because the condenser is in the bottom of the refrigerator. Okay, we got one more component here, the expansion. So the function of the expansion is to further reduce the pressure and reduce the temperature. The expansion is a really interesting component. It's just a long, narrow tube. So its job is to reduce the pressure and return the high pressure into a lower pressure so we can move it over to the evaporator. So it works by what I like to call the highway construction zone analogy. So going into the expansion, we have all the high pressure liquid here. So if this were a highway construction, we have all the traffic backed up. Here's the one lane for 5 miles where everybody's going 40 miles an hour. What happens when you get to the other side of the construction and you see the beautiful 4 lanes of brand new concrete highway with not another car in sight? What do? You step on it, right? You press on the gas. So what are you doing? You're pressing on the gas. You're using energy to speed up and get away from the other traffic. So the molecules essentially do the same thing. So they use energy to get away from the neighboring molecules in what's called an expansion. So their temperature goes down a little bit. So this results in the final cooling. So the expansion, really interesting component. It's just a long tube. They frequently coil it up so it takes up less space. So here's like I say, in the older refrigerators, it's a little easier to see these things. There's one just a coiled up expansion in the back of this old refrigerator. So that's pretty much it. We have the evaporator absorbing heat. Here I'm showing another style of condenser. Sometimes they put it on the bottom. That's where you'll feel warm air on your feet. So we look at the system overall here. You can see that the heat comes in at the evaporator, evaporates the refrigerant liquid, carries it around. The heat is exited or gotten rid of to the room air, and then comes back around to the expansion. So this is our continuous cycle. Heat coming in from the refrigerator interior where you put stuff to cool off, heat going out to the room air in the kitchen. Okay, so let me ask you this question. Let's think about air conditioning. Could you use air conditioning? Suppose you wanted to cool the room off, and for some reason air conditioning wasn't available. Could you just open the door of the refrigerator, let the cold air out, and have it cool the room? Maybe even put a fan to help blow the cold air out. The evaporator might make more cold air as we need it. So the problem with this, as I think some of you are guessing, is that it's a zero-sum game. The heat would get dumped back into the room at the condenser and typically in the back of the refrigerator. So we get cold air coming out the front, hot air coming out the back, no net improvement. But suppose we stick the condenser out the window. We've just invented the window air conditioner. Seriously. So the air conditioner is just a refrigerator with the condenser outside, so that when the heat is exhausted, it's not exhausted back into the room. So the idea here is we have the cold part, the evaporator, in the room, and there's no reason we can't stick the condenser outside the house so the heat goes outside instead of back into the room. So a window air conditioner has the evaporator on the inside and the condenser outside. Now, a couple little key points here. So, usually in an air conditioner, because the compressor gets hot and it's kind of noisy, they usually put that outside as well. And we might want to use some fans to help move the air more effectively past the cooling coils and the condenser coils. So there's usually a fan involved, which a refrigerator doesn't have. So if you just take the cover off of an air conditioner, you'll see components that look very familiar compared to a refrigerator. So it's got the compressor, it has these serpentine tubes here, evaporator, condenser. Here's the coiled expansion. Another view of it from the top here, you can see a little bit better. And you can see here, there's a fan that is basically the one addition to help get more airflow over the evaporator. So this is the cool air going out into the room. And then there's, you just barely see here, the fan outside to help move the outside air across the condenser. And one thing I like about their air conditioner is you can really see that the condenser and the evaporator are really the same component, just used opposite ways. Okay, quick side note about the invention of the air conditioner. Was invented by Willis Carrier, who was at the time, some of you may have heard this story, just 1 year out of college. And he was hired by the Buffalo Forge and Furnace Company in Buffalo, New York, which made forges and furnaces. Buffalo Forge and Furnace was hired by a major newspaper printer in New York City because they said in the summertime, the humid air causes our newsprint to absorb moisture and it gets stuck in the printing press. So we want you to make a furnace to dry out the air in our print room to eliminate this problem. So the management at Buffalo Forge and Furnace figured this is probably not a problem we can solve, but we'll take their money and we'll put the new guy on it. Because he can't really do anything useful anyway. Well, Willis took his assignment seriously and had the classic aha moment when he was waiting for a train one hot night in the summer, thinking about this problem. And he had the realization that the way to remove moisture from air is not to heat it, it's to cool it, because cold air holds less moisture than warm air. In the winter, humidity is lower because it's harder for the cold air to hold moisture. So we realized we don't want to heat the air, we want to cool the air. Now, at the time, this is 1904, refrigeration existed. It was not in every kitchen. It was primarily an industrial process used in warehouses and things. So it was available. The technology was available. So Willis realized, oh, we can use a refrigeration technology, put the condenser outside, cool the space we need, remove the moisture. Okay, in the classic invention story, Buffalo Forge and Furnace said, we make forges and furnaces. We're not at all interested in this idea you have, Willis. So he started his own company, Carrier, which is still more than 100 years later, a major air conditioning, heating, ventilating worldwide company. So that's the story. And now, interestingly too, the name air conditioning was because he wasn't actually trying to cool the air, he was trying to condition the air to get the moisture out. So those were the terms that he was using. The cooling was really just a beneficial side effect, but it's still stuck till today. Okay, so let's go from cooling to heating. The microwave oven. Magic. Put the food in, close the door, press the button. 1 minute later, you have hot food. How does it do that? Okay, this is how the microwave works. Now put your hands together. Twist them. Now push reasonably hard and twist them fairly rapidly. You notice it gets a little warm? Okay, all right, so when you're done today and you talk to other people, you can say, well, what did you do this morning? I learned how a microwave works. Well, how does it work? All right, so we're going to say, all right, this is the basic effect, how the microwave heats food. But first, a little bit about the inventor. So the inventor of the microwave, Percy LeBaron Spencer, born into extremely challenging circumstances. His father died when he was a toddler. He was abandoned by his mother. They were in rural Maine, rural northern Maine. His uncle died when he was still young. So as just a young boy, Percy was left to fend for himself and his impoverished aunt. So he left school to work in the mills and the factories. And then when he was 16, he joined the Navy. And this was now around World War I time. And the latest technology was radio. Now, so Percy was a self-educated person who liked to read science and was self-educating, and he was attracted to the potential of radio, which was the high tech of its time. In World War I was really when radio kind of came into its own, and the commercial radio really started after the war. So we'll leave Percy as a radio operator in World War I and move on to a little bit. We'll come back to him in a second. But the microwave is based on radar. So what's radar? So radar, as we're probably familiar, is used to detect objects at a distance from the radar station. Now, originally developed for metallic objects like aircraft, it's since been expanded to be able to detect water. So like with a weather radar. So how does it work? So it's kind of similar in principle to a lighthouse in some ways. So the lighthouse sends out a beam of light. And we can imagine if we had a mirror somewhere out away from the lighthouse, that it would reflect that light back to the lighthouse. So radar uses the microwave beam, a radio wave, to come out from the source, like the lighthouse, sending out the light beam. The radar antenna is sending out the radio beam. It hits a metallic object like an aircraft, and some of it bounces back, and it detects that bounce back and interprets it as something out there. So what's the radar beam? It's an electromagnetic wave. So we're going to pass out something to help you visualize this. So electromagnetic wave, it's definitely a mouthful, tongue twister there. So what's waving? In an electromagnetic wave, what's waving is the strength of an electric field. Now, normally we're familiar with water waves where what's waving is the height of the water. We see the ripples indicating the water wave. So electric field is similar to a magnetic field. Electric fields are sort of hard to create, but magnets are relatively easy to come by. So Kathy's passing out some magnets. So I invite you to just play around with the magnet. But be careful, they're fairly aggressive magnets. If anybody gets cut, we do have some band-aids. But this, particularly if you separate them and then twist one over, you can feel them pushing against each other. So the magnetic field, something is going on here. It's the force that the magnet is exerting on the other magnet. And it can be quite substantial. But you notice there's a bit of a distance effect, farther away, closer, stronger. But again, they are pretty strong magnets, so you got to be a little careful with them. So if you think about a wave, one way to characterize that wave is the distance between the wave crests. So we call that the wavelength. And the number of waves per second going by, we call that the frequency. But interestingly, the wavelength really determines the property of the electromagnetic wave. So if we have a relatively small wavelength, that's visible light. So small wavelength, our eyes perceive as different color of light. But if we just expand the wave, just stretch it out to a longer wavelength, then we get infrared light, microwaves, and then the radio waves that are used for TV, radio, cell phone, etc. So microwaves are just an electromagnetic wave of a certain distance apart, a certain wavelength. Okay, so back to Percy Spencer. So World War II comes along, and Spencer's out of the Navy. He's now working for Raytheon, which was one of the first producers of radar. The key aspect of radar is what I call the microwave light bulb. So light is produced by a light bulb. The electromagnetic waves for radar are produced by a similar component that emits not light, but radio waves. But it doesn't look too much different from a light bulb there. But Spencer, being the kind of go-getter person that he was, became the director of manufacturing for Raytheon and was actually quite a prolific inventor in terms of the production of microwave magnetron, the key part that produced the microwaves, in large volume, high quality. So prior to World War II, they had radar, they had the magnetron, but they were very hard to produce and took a long time, very finicky. Percy Spencer found ways to mass produce thousands per week that they needed for the war. So pretty prolific inventor in that area. So one day, near the end of the war, or right after the war, Percy Spencer is walking around the factory with a candy bar in his pocket, and he noticed that after he passed by one of the radar sets that they were working on, the candy bar melted, and it didn't just get soft, it liquefied, it turned into liquid chocolate. And he realized, there was an aha moment, something from the radar set is what liquefied this Hershey bar. It makes me think, well, what else is it liquefying? What other parts? And it turns out that other people working around radar had noticed this sort of effect, but didn't really put two and two together. So Percy Spencer said, well, maybe we can utilize this to actually cook food. So they went and got some popcorn. They put it on the functioning radar system, and it popped. So this led to the development of applying the magnetron and radar technology to cooking food in what we now call the microwave oven. So the first microwaves made by Raytheon, because they were using primarily the components they had available for like radar sets, were pretty big. They were 800 pounds and primarily only used in commercial applications like restaurants. But then they teamed up with Amana, an appliance manufacturer, to find ways to make them smaller to become the now ubiquitous household appliance. But how does it work? So the last thing, so where does the hand twisting come in? So this is the key step. This is the trick with the microwave. So we need to look at the water molecule. So we're probably familiar with the chemical composition of water, H2O, two hydrogens combined with an oxygen. Now, the way the water molecule arranges itself, very interesting. It's electrically neutral, but it has kind of a positive end and a negative end. From a distance, they balance out, but close up, we kind of have a positive region and a negative region. So what happens when the microwave is incident upon the water molecule tries to line up with the direction of the electric field. But an instant later, the wave has reversed itself. So the water molecule now says, oh, wait a minute, and turns around to line up with the field going that way. But then it reverses again, so the water molecule has to twist back. Now, these water molecules are sitting shoulder to shoulder with billions of other water molecules that are all trying to do this simultaneously. So what's happening is they're twisting back and forth, bumping into each other, creating friction at a molecular level that results in heat. So this is the analogy. So your hands twisting back and forth are like the water molecules twisting back and forth, trying to align themselves with the electric field from the microwave. So in the microwave oven now, the overall system, so we have the component, the magnetron that produces the microwave. So here's one from a microwave oven. It's not working. It's not plugged in. But so this is the part that emits the microwaves, and it looks a little bit like an antenna or the filament of a light bulb. And so our main components here are the magnetron creating the microwaves. Then we have to get the microwaves to the food. So it travels through the waveguide and pass this around. So here's the waveguide, and it's just an aluminum, like a duct. So the microwave goes in here. The waves get directed along, and they come out there. Passes. The magnetron's a little heavy. So then we have to make sure, so think of it as if we were shining like a flashlight in there. We want to make sure that the microwaves get well distributed over the food. So that's the job of what looks like a fan in the microwave. Some microwaves you can see them, some you can't. In the top, this thing turns actually usually fairly slowly, and that bounces the microwaves around to make sure that it kind of spreads out over the food. And at the same time, the platter rotates to help make sure that the food is exposed evenly to the microwave. And then we need some sort of control system to make sure that they turn the microwave off if you pull the door open before the minute is up. So we can see here the system is just the magnetron creating the microwaves, the waveguide moving it from where the magnetron is in the back to the front, the deflector bouncing it down, and then the food container to hold your food. And so the microwave works primarily by heating water. So that's one of the reasons why things are liquid. Okay, two more here. I want to talk about the electric utility, and then hopefully we'll have time for kidney dialysis. So quickly here, electric utility, you plug something in, press the on button, and it works. You know, presto, magic. Unbelievable. How does it do that? Okay, so the basic effect here, now that you guys are a little bit warmed up, I'm going to give you a bit more complicated task to perform. Kathy's going to pass some of these out. So another thing you can say that you did is you're going to make some electricity with your bare hands. So we have a coil of wire and a magnet. If we wave the magnet back and forth around the coil, you can get a little pulse of electricity to light the light. And there's multiple ways that you can do this. So the idea is you have to move it relatively quickly, fairly close to the coil to get the light to blink. This is the basic effect here. We're making electricity with our bare hands. So this effect is called electromagnetic induction. So there's a bunch of ways to describe electromagnetic induction. The intuitive way that I like to use is the idea that when we have a conductor like a wire breaking magnetic field lines. So if we envision the magnet, the field that it produces, the magnetic field spreads out around the magnet. And normally it's static. So I have this magnet here in its field. But if I break that field or break those field lines with the coil, it produces an electric current in the coil. That's it. That's the basic effect. Okay, well, we have a long way to go here. That's not very convenient to move something back and forth. And notice too, what really matters is relative motion. So I can hold the coil and move the magnet. I can hold the magnet and move the coil, or I could move both. As long as there's relative motion causing the field lines of the magnet, or if you think of the coil as interrupting the field somehow, we get a little bit of a current in the coil. We didn't need the bandage yet, did we? Okay. Good. Okay. We'll push our luck. It's much easier to spin something, to rotate something, than to move it back and forth in a linear motion. So the electric generator, the practical generator, spins the coil instead of moving it back and forth. So we pass these around. So you have a little generator here, and the idea is we need to have the coil breaking the field lines. So an easy way to do that is to turn it. So here's the coil, here's the magnet. These are a little flimsy, but if you turn it, you get to see the red light blinking. If you spin it in the other direction, it makes current the other way, lights the green light. Get these passed out to you. Okay, so those are, you know, like I said, a little flimsy. And if you want to work off a few calories, the different generator here is a bit more durable. These are heavier duty, and you can see that it's the electricity is proportional to speed. So if I turn this slowly, I get a little bit of light, but if I turn it faster, producing more current. And when you do this, you notice that it's actually harder to turn when it's brighter, as would make sense. It's requiring more effort on my part. So these are so you can turn these good and hard because they're more durable. So the practical generator is just a heavier duty version of this effect. So coils and a magnet, and you realize that, well, making electricity really isn't that hard. The hard part is turning the coil. So how do we produce the motion so that the coil and the magnet can, the coil can break the field lines? So, so many of the key utility scale sources of electrical energy are just different ways of how to spin the coil. So let's start with a fossil fuel plant, like this is the Campbell plant, burns coal up in Port Sheldon. So the goal is, you know, how do we spin the coil? So fossil fuel plant says, well, let's burn some fuel like coal, heat water to produce steam, direct the steam to a turbine, so similar to same effect as a jet engine. So the steam is turning the turbine. We attach the coil to the turbine. So then the turbine spins the coil breaks the field lines. We have electric power coming out. So furnace, boiler, steam, turbine, generator. What about nuclear power? Nuclear power, like the one down in Covert, Palisades, that's being reopened, just uses the nuclear energy to heat the water to make the steam. So we replace the burning coal with the reactor using the heat from uranium to heat the steam, to turn the steam turbine, to turn the generator. What about wind? Okay, well, wind, we take the kinetic energy of the air and use it to spin the wind turbine, so like the windmill. So we have the wind turning the turbine, connect that to the generator. So now we're turning the coil. That's producing electrical energy. What about hydro? Okay, let's use the power of the water to spin a different sort of turbine. Same idea, like why spoil a good thing here? We get this turbine spinning, connect that to the generator, that produces electric power. What about a home generator? Okay, you're getting the idea here. Same generator, maybe a little smaller. Now we have a gasoline engine, like a lawnmower engine, spinning the coil in the generator, producing electric power. What about these things? Pedal generators. So the pedaling is what's spinning the coil to create the electrical energy. So all these various sources you see have an underlying similarity in their systems where we have at the end point is the same generator using the same effect that you just experienced in different ways to turn it. So either we have a steam turbine in nuclear and fossil fuel, we have a wind turbine or water turbine, or we have pedal power or the gasoline engine. Okay, quickly, another invention story. So inventor, the person that we can owe a lot of thanks to for this way to generate electricity is Michael Faraday. He discovered this effect. So this effect, the basic effect that we just experienced here, he discovered this in October 28, 1831. And this is known precisely because Faraday kept meticulous notes, meticulous notebooks. Now, he probably doesn't have the household name that other famous inventors like Edison, Tesla, Bell have, but partly because he really was the forebearer, the John the Baptist of electrical energy coming at the beginning. If it weren't for Faraday discovering a way to make pretty much as much electricity as you want, as long as you have something that can spin the coil, like a water power or a steam engine, you can have as much electricity as you want. So his discovery and development of the generator made it possible for people like Edison, Tesla, and Bell to have a source of electricity that they could use. So one quick note on his life story, another really inspirational situation here. So born a poor working class in England, was apprenticed to be a bookbinder. At the time, so early 19th century, the Royal Society of Science in England, which was primarily a society of the aristocrats, were Sir Humphrey Davy, the president of the society, was giving public lectures, kind of like the NPR of its day. They thought bringing the wonders of science to the general public. Well, Faraday attended all the lectures, took notes, bound them. He was a bookbinder, and approached Davy at his last lecture. Now you have to think about it at the time. Sir Humphrey Davy, an aristocrat, Michael Faraday, a lowly working class bookbinder, couldn't just go up to Sir Humphrey Davy and say, "Hey, I really liked your lecture." To get his attention, he presented him with this bound copy of the lectures. Well, this impressed Davy and said, "Hey, clean up around the lab, make yourself useful." Literally gave him a job cleaning the lab. And from there, Faraday became a really extremely productive inventor, particularly in chemistry and electromagnetism. Now, he wasn't really given much credit at the time. And think about, so he was really a path breaker. This is early 19th century England. Think of how stratified the society was along class lines. It was incomprehensible to most people that a working class individual with no formal training could make any kind of a substantial contribution to science. Nonetheless, Faraday was eventually recognized somewhat after his time for the impact of his inventions. I have to give Davy credit for being willing to recognize the talent and to nurture it in this way. Okay, one last thing here. Let's switch to a little bit, somewhat less familiar technology, but still magic, kidney dialysis. So what does it do? Replaces some of the function of the kidneys by, what do the kidneys do? The kidneys filter blood to remove water and excess waste and excess water from the blood. So this kidney dialysis machine on the right there can replace some of the function of the human kidney. It's a not uncommon medical intervention. What's the basic effect? Well, we get a hint here. We want to replace the function of the kidneys. So one of the functions of the kidneys is to filter the blood. So what are some common filters? Well, like coffee filter or tea bag. How do they work? Like a tea bag. Well, the porous tea bag contains the tea leaves. The liquid passes through spaces in the fibers of the tea bag, retaining most of the tea leaves. Now, a key thing about particularly tea is that there are small solids in the tea that will get through the filter, get through the tea bag. So if you look at a brewing tea, and at the bottom of the tea bag, bottom of the teacup, you oftentimes will see a little bit of sediment like that. That's not because you didn't wash the cup well enough. It came from the tea. So you look at a microscopic examination of the tea bag, you see that, well, there's the fibers, and it's easy to imagine the liquid water will get through. But there's also some not too small spaces, and the tea leaves contain particles of all different sizes, and some of the small particles will get through those spaces to form that sediment. That's really the effect that's used in the kidney dialysis machine. So the key component here is the dialyzer filter that is in some ways like the tea bag. So what happens in the dialyzer filter, the blood from the patient is on one side, and the waste products are typically smaller than the blood cells. So there's pores in the filter that are big enough for the waste products to get through, but not big enough for the water molecule, for the blood cells to get through. The other side of the membrane here, as it's called, has the dialyzer fluid that's absorbing those waste particles. So it's the particles come through and get carried away by the dialyzer fluid. So this is like your urine. It's absorbing the waste particles to get rid of it. Okay, so a bit of practicalities here. So we need a lot of surface area to accomplish the cleaning of the blood in a reasonable amount of time. So that filter is actually filled with very small tubes through which the blood flows on one side, the dialyzer fluid flows on the other, and each tube is made of this membrane with these holes that are just not too small, not too big, just right to retain the blood cells on one side, let the waste go through. So the blood generally flows through the tubes, and the dialyzer fluid flows on the outside of the tubes. We've kind of got it halfway figured out. What about a pump? How are we going to push the blood through this filter? And there's pumps around, like some pump or a coolant pump in your car. These are called centrifugal pumps. And the way they work is they have veins or impeller, as it's called, that essentially push on the liquid. So in a sump pump or coolant pump in the car, liquid comes in the middle, and these rotating veins push that liquid around, increase the pressure, and goes out the outlet. Maybe not the best choice for blood. A couple of reasons why. A pretty aggressive process that could damage the blood cells. And also, you can imagine it would be difficult to clean. We're going to use this on another patient. You've got to clean out, sterilize them from the previous patient. Maybe not ideal. But there's other ways that we can move liquid material. Think about toothpaste. How do you get the toothpaste out? You squeeze it, right? You squeeze the tube. When you squeeze the tube, it pushes out the toothpaste. This leads to a different type of pump called a peristaltic pump that uses this process. It just keeps the blood or the liquid in a flexible tube and has a mechanism here that does the same thing your hand does when you squeeze the toothpaste, pushes on the tube, squeezes it down, and forces the liquid out the other end. So this is great for biomedical applications because the liquid, the blood, stays in the tube, never comes in contact with the mechanism. We can use a new tube for a new patient. Tubes are relatively easy to come by and relatively cheap. So here's a view of one. You can see the tube here and the little rollers that go around and push on it. Here's an animation of one. You can see that it rotates, it pinches off a bunch of the liquid and pushes it around out the other side. So these are widely used in biomedical applications for contamination purposes. It's also relatively easy to determine how much liquid gets pushed through because you just have to count rotations and you can determine. So if you're administering a certain amount of something at a certain rate, we don't need high pressure. We don't need high volume like in, say, putting out a fire. Okay, so just about done here. We can see how the kidney dialysis system uses these two key components and the effects that they provide to create an overall system. So the dialysis device will also include some monitoring of the condition of the blood. So the blood plus waste comes from the patient. We're measuring the pressure. It's pushed around by the pump. We want to measure the inflow pressure going to the dialyzer, the cartridge, and then measure the pressure going out because this is what connects back to the body. Sometimes air can get in. So just like in scuba diving, we want to make sure we remove any air from that might get into the blood before the clean blood is returned to the patient. Okay, we're done. Summary here. It's still magic, okay? You know, even if you know how the magician got the rabbit into the hat, you know, we could still know how the trick was done and appreciate the show. So the magic that's achieved by the system of components using physical effects, their form, their physical shape, enabling the function, combining into a system as a team, producing a net result that's more useful than the individual components, more useful than its parts. You know, we can still appreciate all that, and still think that it's magic. Okay, I think we're done here.
Thank you. Some questions?
Kind of skipped over questions earlier, so if anyone has any questions on
Yep.
any of the parts, yeah.
Okay, well, hold on a second.
I always like it. I feel like I've learned something and I've learned a bunch today in that.
Great. Don't forget this.
Right, exactly. In that. Couple questions come up. I'm sure there's plenty from everybody else. But the thing that struck me when you talked about the microwave oven and its effect on water is obviously it has effect on other things. Anybody who's tried to pick up a ceramic plate out of a microwave realizes there's a lot of heat energy that goes into there. Is it a broader spectrum or acts on multiple molecules, or am I missing something here?
Yeah, so it's primarily working on the water molecule, but the other, like a ceramic, there's still molecules in there that'll be affected, not to the same extent. The thing that, you know, honestly concerns me is, you know, our bodies got plenty of water, and the microwaves, they're shielded so that they don't release microwaves, but we can't see them. So, you know, personally, it's always not a bad idea to stand a little bit back from the from the microwave when it's doing its thing, because we don't see them, only their effect, and it'd be too bad if the effect is something on your body. Does it work? Oh,
I said, you hold a cell phone right next to your ear and it's outputting microwave. That's why it heats up.
yeah, so that's another thing. So the frequency of the cell tower signal is relatively close to the same frequency of the microwave. And this is a question that's finally being honestly looked at in the scientific community, is the effect of the microwave on the human body. Because when you're talking to someone, this is transmitting microwaves, some of them into your head. So it's a question of the extent of that exposure. And my personal opinion is it was not really studied enough when cell phones first came out, but it's finally being re-examined.
Yeah, two questions here. Here's the
Sure.
first one.
I have a comment about two of your slides and then a question. I think of Faraday as a Faraday cage at the current stage, where if I don't want the government snooping on my cell phone, I put it inside a microwave and close the door. It's a Faraday cage and no RF could get in or out.
Right, that's actually another one of his inventions, was the idea that a complete metal enclosure prevents any electromagnetic waves from getting into it. So the electromagnetic waves cannot penetrate a completely conductive enclosure. So the microwave oven is exactly that. So to keep the microwaves in, the idea is that the thing should be a metal enclosure, but these pouches and things you can put your phone in are similar. They're a conductive enclosure, so that once the phone's in there and it's completely encased, no radio waves, no electromagnetic waves can get in or out. So yeah, I think
You know, the
Yeah.
entire bridge of an aircraft carrier, for example, is one giant Faraday cage. And now to my question, if I may, I
Yeah.
go back to the jet engine. In terms of maximum efficiency for fuel burn, the higher you go, the less oxygen. So you have to push more in to get to thrust. But at what point does the reduced drag at an elevation allow for maximum fuel efficiency at, say, 500 knots?
Yeah, I think that's a key thing with those military aircraft is the trade-off between going higher for reduced drag, but at the same time, you're losing air density. So we're fighting against that. And I'm sure, by now they've probably figured that out pretty carefully. And also the atmosphere density, particularly high up, changes between day and night. So there's probably an effect between daytime and nighttime conditions in terms of the density in the upper part of the atmosphere. But you're absolutely right. There's definitely these trade-offs that kind of result in a practical limit.
I have one last question for you. You've been teaching self-declared non-scientists for a few decades now. Can you give us an appreciation of the perception of technology by your students in, say, 1995 compared to those in 2020?
Yeah, well, definitely it's had an effect. I think the video and everything has become kind of assumed. So in 1994, lab instructions were all text. Now, and at some point, literally in that time span, I gave out these instructions that I had been using, and students said, we can't follow this. So I had to switch to adding video, and now they pretty much want things in video form. So there's been a shift in terms of the preferred mode of information transfer.
So, great class. You need on your slide about electric generation, you need to add one additional type where you take the jet engine and marry it with a generator, because that's what goes on about a quarter mile away over here at the energy park. There's two jet engines that drive the generators. Plus, there's a steam generator as well.
Right. The gas turbine. Yeah. Thanks. Good point.
And on that note, we thank you very much for being here today. If there are additional questions, you can join us.